Hello dear students, welcome back to the lecture series on theory of semigroups with course code MMTE 405. So we continue this lecture with regular T classes. As we have seen in previous theorem, let me first write down the statement of that theorem. In previous theorem we have seen that in previous theorem we have seen that if B is in some D class, B belongs to D, where D is a D class, such that E belongs to the intersection of R class and L class, R class of A and L class of B. B is in this D class D, such that E belongs to this R class of A intersection L class of B, and F belongs to L class of A intersection R class of B, where E and F are idempotents. E and F are idempotents. Then theorem says that there exists an inverse A star, which is in HB, inverse A star in HB of A, such that A star is equal to E and A star A is equal to F. A star A is equal to F. And here this A star in this theorem, this A star is it is precisely equal to Fxe, where this Ax is equal to E. This we have seen in previous lecture. And note that here this E belongs to Re. It implies that A belongs to Re. So from this you can see this E belongs to Re. E belongs to Re. Sorry. This A belongs to Re. A belongs to Re. And here you can see that this A belongs to LF. So it means that it belongs to Re intersection LF. So we are using this actually, this fact, A belongs to Re intersection LF, then we see that there exists an inverse A star of A which is an HB, such that A star is equal to E and A star A is equal to F. So let me write down the statement of the next theorem, which is statement is let E, and it's actually a similar type of theorem. Let E and F are idempotents. Let E and F are idempotents in semigroup S, in a semigroup S, in a semigroup S. Okay, in a semigroup S. Then these two are equivalent. E and F, they are D-related if and only if. If and only if there exists an element. A in S, and an inverse A dash of A, and an inverse A dash of A, such that this A dash is equal to E and A dash A is equal to F. A dash A is equal to F. So these E and F, they are derelated if and only if this holds. Okay. So let me write down the proof of this theorem. So first we assume that E and F are derelated. Okay. So E and F are derelated. Proof. Assume E, F, they belong to D class. Okay, they are derelated. They are derelated. Okay, so what's T relation? This is actually R composition. This is actually R composition. And so it means that then by definition of composition, then there exists A belongs to S such that A it is R related, and then A F is L related. That's the definition of composition of the relation is. Okay, so this gives that A belongs to RE and F belongs to LF, so which implies A belongs to RE intersection LF. So now, as in the previous theorem, whenever A belongs to RE intersection LF, done in the previous theorem, whenever A belongs to this, then there is an inverse. So therefore, as in previous theorem, there exists A dash inverse of A in S such that A dash is equal to E and A dash A is equal to F. So thus whenever E and F are derelated, then we can find two elements A and A dash, so that A dash is equal to E and A dash A is equal to F. So now let's approach converse. Conversely assume that there exists A dash in S such that they are mutually inverse of each other, that such that A dash is inverse of A and A dash is equal to E, A dash A is equal to F. A dash A is equal to. We need to show that E and F are derelated. E and F are derelated. So let's see how they are derelated. Now this TA. So since our S is the union of D classes where A belongs to S, or you can say B belongs to S. B belongs to S. So this means this A is in some D class. So we have this A belongs to D class of A. A must be in some D class because this is the union of D classes, and A is in S, so it must be in some D class. Exactly, it is in this D class of A. So there is no need to write this actually. Can say this A is in D class of A. So now since this A dash, it is an inverse of A, it belongs to V of A. V of A means the set of all inverse of A. A dash belongs to V of A. Then again, you can see this. So then this A dash A is equal to A. So and A dash is equal to A dash. Now look at this. A dash is equal to E. So E into A is equal to A. And one more thing, which A dash is equal to E. Now see this one. there are two elements A and A dash such that E is equal to A dash is equal to E. So which means that this implies E is or related to A. So which means that this means that okay. So E is or related to A. Now this one A dash is equal to F. Again this A dash times F is equal to A dash, and this one it's A dash A actually. It's is it A dash A or A dash? Oh, so I want actually this A should be L related to E. A should be L related. A should be L related to F. L related to F. Okay. So here A dash is E. Okay, but A dash A is actually F. So it's okay. A dash A is F. So here I can see this. A times A dash A is F. A times F is equal to A. A times F is equal to A. And one more thing, that is A dash A is equal to F. So for F and A we have two elements A and A dash such that F is equal to A and A dash A is equal to F. So this means that there are two elements which exist on left side actually. So that means this A comma F, they are related to each other. Now we can compose these two. A belongs to R, A belongs to L. So that means EF, it belongs to, this gives E comma F belongs to L composition R. What's L composition R? It's equal to D. So that means E and F are D related. E and F are D related. So this completes the proof of this theorem. This completes the proof of the theorem. The next theorem, it's similar to one of our previous theorem. Let me write down its statement, its proposition. It states that if H and K are two H groups, if H and K are two H groups, so that means they are classes, H classes as well as their groups, subgroups of S. In some regular D class, then H and K are isomorphic. Then H and K are isomorphic. The proof is it's similar to the proof where we have shown that the proof is similar. Or you can see its proof on the book, the Fundamental Theory of Semigroups, and if you want to see it, you can see it's a proposition number 2.3.6, and the page number is 54. And the proof is similar to the proof where we have seen that the cardinality of HA is same as cardinality of HB. So that means there is one onto mapping from this. So let me denote this by HA class by H, HB class by K. So there is a bijective map between these two H and K, between these two H classes. One is H and second is K. So there is always bijective map. But you just now here H and K are there also groups. So you need to show that they are isomorphic. Means this bijection should be homomorphism as well. So then you can say H and K are isomorphic. It's very simple. You can see it. And proof, the rest of the proof is similar. to the proof of the theorem, where we have seen that this H class of A and H class of B, there is bijection between these two H classes. So that bijection, you need to show that bijection is also homomorphism. Then we can say this H and K, they are actually isomorphic subgroups of S. The next theorem, which is in fact the last theorem of this regular D classes, the proposition is let A and B are elements in a D class T. Let A and B be elements in a D class. It's a D class, not regular D class. In a D class D. Sorry, D class D. It's a simple D, not recursive T. Then AB, it belongs to RA intersection LB. RA means R class of A, LB means L class of B. If and only if LA intersection RB contains an idempotent. A and B are the elements of some D class D. Then you need to show that the product AB, it belongs to this intersection R class of A and L class of B, if and only if this intersection where this AB sits, this intersection must contain an idempotent. And conversely, if it contains an idempotent, then this intersection must contain the product AB. Proof. So let's assume that AB belongs to RA intersection L. So this in particular, this implies that AB, it's R related to A and AB, it's L related to B. So from this we conclude there exists the right side in S1 such that ABC is equal to A. And with the help of this equation, there is a translation. So thus there is a translation. There is a right translation. Right translation. Row C, because there is C. From this right translation is from LB. Sorry, it's a simple LB, because it's a class now. LB to LA. Actually, the translation is from LAB. Okay, if you can see, it's actually AB, LAB to LB. Which is defined by, because this is already discussed, whenever we have this AX equal to B, then we define or AX equal to B, then we define a translation rho S from LA to LB. Okay, so here this A is replaced by AB. Sorry, B is replaced by AB. There's a translation from LB to LA actually. So this B, our B is here AB. Okay. AB times C equal to A. So I want to recall that translation here. It's actually this: if AS is equal to B, then the translation rho S is from LB to LA. Here it's ABC equal to B, so there is a translation rho C from it's A here. From this AS equal to B, okay. So it's a translation from LA to LB here. A is equal to B. If there is A, this A is equal to B. So A, LA to LB, okay? LA onto LB. This is actually bijection, LA onto LB. So now here, this will be the translation from LAB onto LA. This is LAB onto LA. So where this translation defined by rho s of x is equal to what? It's equal to ABX. ABX. This is the definition of this translation. In fact, sorry, it's not like this. It's rho c of x equal to xc. Right translation. Now, this translation is from LAB onto LA, but LAB is same as, look at here, LAB is same as LB, because AB is related to A, so therefore this rho C is a translation from LB onto LA. So this is here bijective translation. Bijective. Okay. Now, actually, I want to see that this rho C is bijection from HB onto LA intersection of B. This is the bijection that I want. Is bijection. Okay. So I will see that the image of any element from HB is here actually, and the reverse is simple, that it is actually onto. So let's check that let x belongs to HB, which is equal to RB intersection LB. If x is in LB, then its image is in LA, because this is the bijective map. So we assume that if x is in LB, then there is nothing to prove. Then rho C of x, it belongs to LB. It belongs to LB. Okay. It belongs to LA. Sorry. So LB onto LA. But so x is in this, so then so this means let's